I thought I'd look at number 87 on section 3.5. This problem shows us a picture of the comparison between Newton's first law of motion of a particle and Einstein's special theory of relativity. Newton says that a particle, once it gets going, it's going to continue going until a force acts to stop it. So in theory, it would just keep getting. If you had a particle and you kept speeding it up, you could speed it up until it was, just infinitely. But what Einstein said was that when a particle approaches the speed of light, it's never going to get faster than the speed of light. And so that's what this graph shows here, is it's just comparing those two things. And so what the book wanted you to do was write a limit statement that describes each theory. So for Newton, which is represented by that green N here, as we take our particle, and this is going to be a function of time, n of t, is if we want to look at that function as a function of time, we could write it as n of t and e of t. The limit for the function n as time approaches infinity is if we're just, over time, we're speeding that particle up. What Newton said was that it approaches infinity. And remember, Newton was the guy that invented calculus, so that's kind of also an interesting thing. I don't know why I'm kind of writing things backwards, so let me just pick black here for Einstein. Einstein said that as time increases and the speed of that particle increases, that what the velocity of that particle is going to approach is the speed of light, which is this c up here, the speed of light. So this is all they wanted you to do on 80. Okay, let's look at problem number 88, and this is showing a graph, and it's the temperature of an apple pie that's cooling after it's been removed from the oven. And the x-axis represents time. As time passes, what happens when you cool something? Well, it pretty much cools down to room temperature, doesn't it? Okay, so if you look at this graph, they're assuming room temperature here is 72 degrees. So they ask us some questions. Find the limit as t approaches 0 from the positive side. Okay, so if you were let me make I'll pick a color like blue. You're coming up on 0 from the positive side. What is it approaching? It's approaching 400 of the temperature. What's the temperature approaching? That would be 425 degrees because it actually starts at 425 degrees, right? This limit represents the temperature that the pie was when you took it out of the oven, or the pie was cooking at 425. So it's at this when you took it out of the oven, temp upon removal from oven. That pie. Okay. So this is just these are kind of easy, fun questions, actually. And then they say, okay, what's the limit as t approaches infinity? As infinite amounts of time pass, what's the temperature going to be? Well, if you look, the graph shows us what's happening is that things cooling off, and it's going to approach room temperature, which was 72 degrees. And that represents what room temperature is, that the pie is going to eventually, that all particles eventually are going to kind of come to the same temperature if left in contact with each other long enough. So it's going to come to room temperature. Okay, now 105 asks us a question. It's basically true or false, and if it's false, they want an explanation of why it's false. And I'll be honest, if you had a hard time with this at first, maybe eventually I'll come to a better understanding of it. It asks you if the derivative is greater than 0 for all real numbers x. So we'll take the derivative, it's a positive number, like 2, okay? Then is the function increasing without bounds? We know that with certain functions that's true. If you think about it, what if I had a line? The function is increasing without bound. Let's say the slope of that line was 2. Well, in this case, yeah, that's a positive. The slope is the same thing as the derivative, so it's got a positive derivative. The function is increasing. But is that true for everything? And so they say basically no. Here's why. I can kind of use this same idea here. And this is actually the one the answer key gives. I didn't come up with it myself. I just kind of trying to make you make a little bit of sense out of what they gave. They say let the function be something like we've had in some of those earlier problems where it's 2x over the square root of x squared plus 2. Do you remember on all these problems that these things had a horizontal asymptote, anything that looked like this? As a matter of fact, you could put this one in your calculator right now. and see that it has a horizontal asymptote of 2, okay? So if I went and I took the limit of this, which is, the limit and the derivative usually are the same thing, okay? If I did that, do you remember that what happened is I'm actually even algebraically going to get a 2. This one is not as tricky as like number 29. When it approaches negative infinity, that's when it gets all tricky. But if we divide everything out by the highest power and we take the limit, we get 2, the limit as x approaches infinity, of 2 over, this would be square root of x squared divided by x squared plus 2 over x squared. And when you do your evaluating and you plug your infinity in, this becomes 1. And this infinity, this whole term goes to 0. So you end up with 2 over 1, which is 2. So this has a positive, it has a positive derivative. It has a positive slope. But it has a positive limit. But with if you look at it's a positive limit. But if you look at the function, it definitely does not increase without bounds. It approaches a horizontal asymptote of 2. So this is actually false. And that's what they wanted you to see is, you may have something simple like this where that's true, but then really this function here is not too different. I mean, it has a limit of 2, which is similar to our slope. It's not exactly the same thing because we know that the slope on a function at any different point, at any particular point might be different. The slope might be different, but it does approach 2. And so we have a horizontal asymptote of 2. That means that no, this thing doesn't increase without bounds. And we can actually see that if we put it on the calculator.